Hi, my name is Jesus,
Hi, my name is Yeamlak.
and today we'll show you how to derive the unit circle and remember it in easy steps. So first, the basics.
Okay, so when we say a unit circle, we're talking about a circle where the radius is 1. This could be one of anything. So this could be 1 feet, 1 inches, 1 centimeters, as long as the unit is 1. Right here we have the diameter. The diameter is represented by 2r, or it's twice the length of the radius. That's the center. The center is called O. It gives the circle a definite name. And C describes the circumference, or the parameter of the circle. Here are some important notations to understand. Circumference is described as 2 pi radius, or 2 times pi times the length of the radius. And in this case, the radius is 1, so the circumference would be 2 pi. Important stuff. And the diameter, like I said, it's twice the length of the radius, meaning in this specific case, or in the unit circle, the diameter would be 2 times 1, which is 2 of some unit. So in a unit circle, it's important to note that the circumference is 2 pi and the diameter is 2 of some units. Over here we have the classifications. So in trigonometry, it's important and key to understand the special angles. So the special angles are found here. So there's 0 degrees, there's 30 degrees, there's 45 degrees, 60 degrees, and 90 degrees. These are the special angles, and from these angles we could find the remainder of the angles in the circle, in the unit circle. So in order to find these, we use an important concept called reference angles. Reference angles, so basically these are reference angles. We base off what these angles are based on the values of the special angles. That's what makes them so special. So let's start with this one, right? As you can see, this has some form of, this looks like some form of the Cartesian coordinate plane. So if you could isolate this looks like a Cartesian coordinate plane basically inscribed in a circle, right? So when you look at this, you'd realize it's common that this is the first quadrant, this is the second quadrant, this is the third quadrant, and this is the fourth quadrant, right? So the special angles are designated and located in the first quadrant of the Cartesian coordinate plane. Now we look at the second, third, and the fourth quadrants. So what's important about the reference angles, like I said, is they are designated formulas for each quadrant, and they use the concept of these angles to map out the values of these other special angles. So the formula to note or to remember for the second quadrant, it's going to be angles for Cartesian coordinate plane 2 is equal to 180 minus your reference angle. So 180 minus your reference angle, for example, if you have reference angle 30, 180 minus 30 is 150, which is this specific one. What are they called again?
The what?
These ones. They're supplementary, complementary. Forget it. Okay. Continuing this, for 45 degrees, it's 180 minus 45 degrees, which is 135, and 180 minus 60 degrees, which is 120. So and for the 90 degrees, you have for the 0 degree, you have 180 minus 0, which is just 180. Right. When using the special angles in the first quadrant, we're trying to find the coterminal angles regarding the first quadrant degrees. So for the third quadrant, the formula to find the coterminal angle of the special angles in the first quadrant, we use this formula. So the angles designated in the third quadrant can be found by adding 180 to the reference angles. So we have 30 degrees right there. So the coterminal angle in the third quadrant for 30 degrees is going to be 180 plus 30, which is 210 degrees. Let's just for the coterminal angles in the third quadrant, for these, for 45 degrees is going to be 180 plus 45, which is 225 degrees. 180 plus 60 degrees would be 240. And finally, 180 plus 90, it's going to be 270, right? Okay, so finally, we're in the last fourth quadrant, and for the fourth quadrant, we're going to use the formula. The fourth quadrant is 360 minus the reference angle. So, following 270, we're gonna use the reference angle 30. So 30 plus 270 is gonna be 360 minus 30 is gonna be 330, which is this angle. 360 minus 60 is gonna be 300, which is this angle. And 360 minus 45 is going to give you this 315. So that is all the angles and all the coterminal angles located in the unit circle.
Alright, so now that we've shown you how to get the angles in degrees, you might be wondering, well, how do I get them in radians? You know, college courses or any course basically at all uses radians. So an easy way to actually remember this is pi divided by 6, pi divided by 4, and pi divided by 3. So if we write these down, these are our angles. They are actually equal to 30, 45, and 60 for the first quadrant. These are the same angles. Now you might be wondering, well, how do I get these angles, you know? Is there an easy way? Yes, the exact same thing. You want to do 3, 4, and 6. You just want to remember that. All you want to do is remember this. A special thing about the unit circle is that most of the actual properties are reflected. So as you can see, this side is actually reflected onto that side, and this entire thing is reflected that side. So you can remember unit circle being reflected both ways, I guess hot dog and hamburger style. So we want to note down again the 6, the 4, the 3 reflected, or from 3 to 3, 3, 4, and 6. Okay, so now that we have these are actually not true, except this one. This is the only quadrant that you don't have to do anything about. So just remember, same. So now for this quadrant, remember minus. So what I mean by that is taking the denominator and subtracting 1, only 1. So this radian would be 2, 3, 4 minus 1, 3, 6 minus 1, 5. This is the radians for the second quadrant. For the third quadrant, I said plus. So again, plus 1. 6 plus 1, 7. 4 plus 1, 5. 3 plus 1, 4. That's a bit blurry. Okay, now that we have written the minus and the plus, how do you get the other one? Prime. So from here, just remember what's the next prime number from the last. So looking at the 4, what's the next prime number that comes out? 5. Prime numbers are numbers that can only be divided by each other. So the next number will be 7. And lastly, 11. Like I stated before, all of these angles are actually equal to their degree. So 11, that would be 330. This radian will be equal to 300, same as 315, on and on and on and on. I think it's a way to actually remember or just to come up with all the degrees will just be by adding 30. As you can see, 30 to 60, the difference is 30. The difference for this one is 15. That goes along with every single one. So 30, 30, 30 with the 90. Again, 30, 30. And from here, the difference from this one to this one is 15 or 45. Another way to remember the 45 is that it goes from 45 to 90 to 135. All right, so now I'm gonna show you how to remember coordinates. An easy way to do this is by using the left hand rule. Using your left hand, you will basically imagine it as the first quadrant of the unit circle.
God.
This right here, 0. This right here, 30. This right here, 45, 60, and 90. Thumb is 90, and your pinky is 0. So you might be thinking, well, how do I find the coordinates? Using your fingers, you can plug it into this formula. Let's find the coordinates for 0. The left fingers will represent the x-axis, or the cosine, and the right fingers will represent the y-axis, the sine. So here, the x-axis for 0 is 4 divided by 2. So plug it in there. Square root of 4 is 2. 2 divided by 2 is 1. So right here, you also have that. Since there's 0 fingers on the right-hand side, we will call that 0 because you can't do anything with 0. All right, now let's find the coordinates for the 30 degrees. As you can see, we have on our left side 3 fingers and on our right side 1. So let's plug that in. 3, square root of 2, comma, 1, square root of 2. That simplifies to 1, and we'll keep that like that. This is the next coordinate for 30. All right, now let's try 45. There's 2 fingers on each side, so we'll know that they'll have to be the same. So again, square root of 2 divided by 2, since they're the same side, there's 2 fingers on the left side, there's 2 fingers on the right side. Square root of 2 divided by 2, square root of 2 divided by 2. All right, now we're left with 60 degrees. We have 1 finger on the left hand side and 3 fingers on the right side. So square root of 1, again, 1/2, 3, square root of 3 divided by 2, the same thing. You might notice a pattern here. It's the inverse of 30, and I'll show you why that is later. All right, lastly, we have the 90 degrees. Plugging that in, we have 0 fingers on the left side, so 0. And on the right side, we have 4. Again, you like like 0 degrees, 4, the square root of 4 is 2. 2 divided by 2, 1. This is the coordinate for y. So that is an easy way to remember all your coordinates on the y side, on the first quadrant. To find the coordinates on the left and the fourth and the third quadrant, like I told you before, we basically reflect it. Since we know that our quadrants are positive, positive, negative, positive, negative, negative, and positive, negative, we could just apply this to these exact same coordinates.
Derivation, okay. Alright. Okay, so now we have the isosceles triangle, and an important key thing about the isosceles triangle is we can use it to derive what the values of the special right angles are. So, the special right angle specifically found in the first quadrant. So, how the derivation came from. Alright, so right here we have a right triangle, but right here both the angles are the same, hence it's an isosceles right triangle. So let's assume that the hypotenuse of the side is 1, right? So we know that these two sides are the same, so let's solve for these sides. So when we're solving for these sides, we could use the Pythagorean theorem to calculate the values of those sides. So we have x squared plus x squared equals 1. So that would be 2x squared equals 1. X equals the square root of 1 over 2. So x right here is the square root of, or 1 over the square root of 2. We have to use rationalization to find that this is going to be, we have to use rationalization so that we don't have a square root at the bottom. So that would be square root 2 over 2. That's the side length, right? Okay, so now we have the side length. Now we're trying to find the value of theta right there. So another property of isosceles isosceles triangles in general is that their base angles are the same. So this base angle and this base angle are the same. So we know that the sum of the angles in the triangle is 180. So we have theta plus the 90 degree right there would give us 180 degrees. And we know theta plus theta is 2 theta, and 180 minus 90 is just 90, and theta equals 45 degrees. So I'm gonna erase all this. So we know theta is 45 degrees. So on the unit circle, it would look something like this. So we have the unit circle, that's a funky circle. The center is right there. We'll draw our Cartesian coordinate plane inside the, this is our rough sketch. So right there would be the value of 45 degrees, right? So now we have all this. So now we're trying to find the values of the sine theta and cosine theta, specifically sine 45 and cosine 45. So how we're going to do this is we're going to use the trigonometric identities. So we know that sine theta is going to equal this length, the opposite, over the hypotenuse. So we have the opposite over the hypotenuse. I'm gonna clean this up real quick. We know side length is square root 2 over 2. Forget that. So now, generally, we're gonna do this. The sine of 45 degrees must be equal to the opposite, which is square root 2 over 2, over the length of the hypotenuse, which is 1. So sine 45 would be anything divided by 1 is just the number itself. So we have square root 2 over 2. That is the value of sine 45. Now let's find the value the value of cos 45, the cosine 45. Cosine 45 is, when you write cosine, it's going to be the side length adjacent to the angle designated. So we have 45 degrees. The adjacent side would be this side. So this side is also square root 2 over 2, since we already solved for x. So this is just going to be cos of 45 is going to equal the adjacent, which is this side, square root 2 over 2 over 1, which is just square root 2 over 2. So that is how the values for the cosine and sine of 45 degrees were created. That is one way of using the isosceles right triangle to derive the values of cosine 45 and sine 45. And that is why it makes it a special triangle. You can easily solve for the values of cos 45, unlike the values of sine 15. Yeah. Okay, now we're going to derive for the 30 degree angle and the 60 degree angle. Okay, so let's begin. So right here, what we have is an equilateral triangle, and properties of the equilateral triangle include all the angles are the same, meaning it's all the angles are equiangular, and also all the sides are equidistant, meaning they're equal sides and equal angles. So how are we going to derive the Pythagorean identities? So again, let's assume the side length is 1, because that would be easier than to calculate for values like 30 or 65. Doesn't matter. Okay, so first what we're going to do is we're going to draw, or we're going to visualize the height of said triangle. Alright, the height is going to touch the base of the triangle at the right angle. Now what we're going to do is, after we have visualized our height, we know that since this is an equilateral triangle, another unique property is the height bisects one of the sides. So whatever the total side length is, it's going to be 1/2. This side is going to be 1/2 of the original distance. So since we assume that the original distance was 1, this is going to be 1/2, and this is also going to be 1/2. All right. So now what we're going to do is calculate or find the side. We're going to find the height, or the height length. So since we know this is 1/2, and since this is an equilateral triangle, all these sides are 1 unit. So now we know the side of the triangle and also the base of the triangle. Now what we're going to use is very famous, the Pythagorean theorem. So we have, which is a square plus b square equals c square. We did something similar like this for the isosceles triangle. So we're trying to find this side. So we're going to use a square plus b squared, which is 1/2 squared, equal to 1 squared, which is that side. Now we solve for this. So we have a squared equals 1 minus 1 over 4. A squared equals 3 over 4. And then a is going to equal to square root 3 over 2. So that is what our height is. I'm just going to erase this. This side is going to be square root 3 over 2. So when we discussed the equilateral triangle, I stated that it's equiangular, meaning all the angles add up to 180 and all the angles are equal. So you have side lengths A plus B plus C, but if all of them are similar, then we can just say they're just 3 times angle theta, which equals 180, and theta is just going to be 60 degrees. So the angle for any equilateral triangle is always going to be 60 degrees. So this is 60 degrees. Also here 60 degrees, and 60 degrees right here. And like the side length the height also bisects the 60-degree side length, the 60-degree angle. So we're gonna have 30 degrees here and 30 degrees here, and we have our 60 degrees there. So we're gonna use the trigonometric identities to calculate the trigonometric values. So let's start with 60. Sine of 60 degrees is going to equal to the opposite over the hypotenuse. Hypotenuse is the square root of 3 over 2 over 1, which is square root of 3 over 2. Cosine 60 is going to equal to the adjacent over the hypotenuse, which is 1 over 2 over 1, which is just 1 over 2. And finally, and then now we're going to calculate the values for the 30-degree mark. So the 30-degree angle right there, the sine of 30 degrees is going to equal to the opposite over the hypotenuse, which is 1 over 2 over 1, which is just 1 over 2 simply. And now the cosine of the 30-degree mark is going to equal adjacent over the hypotenuse, which is square root of 3 over 1 or square root 3 over 2. So now, as you can see, we have the sine, cosine values of 30 degrees and 60 degrees. Like I said, what makes these angles, the 0-degree angle, the 90-degree angle, the 30-degree, 60 degrees, and 45 degrees angle, what makes them so special is you could easily calculate, or you could easily find the values of their sine and cosine counterparts. That is what makes them special.
Right. That was a lot. Now I'm gonna wrap things up. So, what Yeamlak said, that this was 1/2, and that this was square root of 3 divided by 2 for the 60, the 30-60 triangle, which also repeats here. This being for the first triangle, this being 30. For the second triangle, this being 60. Again, these values are flipped, so we have 1/2 here and 3 divided by 2 here. So what that means is that for 30 degrees, the y value would be 1/2. The x value would be root of 3 divided by 2. As you can see here, this being the side of the x, and this being the length, the y. Again, since it's the inverse, it's actually the same triangle, we can find the value for the x one, 1/2. The y value, square root of 3 divided by 2. That's the coordinates. Wrapping things up on the 45 triangle, since I already said, this is 45 degrees. This is actually also 45 degrees, and this is 90 degrees. And we said that this side was square root of 2 divided by 2. Since they're both equal, it's also going to be square root of 2 divided by 2. And the height and length, or the x and y, square root of 2 divided by 2, square root of 2 divided by 2. So that is how you get all the coordinates for the unit circle. We also know that this is 1, 0, and this is 0, 1. With this being the height, you don't move right or left, you go up, it's 1. You don't go up or down, you go right, it's 1. This will also be reflected with your corresponding negative and positive signs. Hopefully you learned something today. Put it in practice. Try to fill this out, find the radians, find the coordinates, find the degrees, and try to go through it. All right. Well, thank you.